In this video, we'll continue our discussion of section 4.1. This is preliminary theory for higher order linear diffuse. All right, so what we're going to work on now is we're heading towards the non-homogeneous case. So we got to be very careful here with notation because it gets a bit tricky. All right, so let y sub p, this is not the same thing we've been talking about. Y sub b be any particular solution to the non-homogeneous linear nth order diffq. Struggled there. But notice that this is the same thing we're talking about on the left side, but all that we're going to have now is we're going to put a function over there on the right, just something with just x. All right. So if y sub p is a solution to that, and then now this changes, y sub 1 through y sub a is the fundamental set of solution to the associated homogeneous differential equation. So it would be the exact same differential equation, except for we put an equal 0 there. So if that's the case, and I have a particular to the non-homogeneous, and I have a fundamental set of the homogeneous, then I actually can come up with the general solution to this case by, okay, and then take a look here. So this is the fundamental solution set, right? That's what we were just working on. That would be that fundamental solution set. We would find that with the method that we just did if we had the set of solutions. And then this part here is that particular solution given from the non-homogeneous. So as long as I have a particular solution from the non-homogeneous, and then I can get the general solution for the homogeneous, I can put them together as a general solution for my original diffie. It's a lot, right? All right, this is going to be the general idea moving forward. So if you're still kind of hazy, it's going to be okay. So let's take a look at an example and we'll start piecing it together. We're just going to verify here, given the two parameter family of functions, is the general solution of the non-homogeneous differential equation that they gave us this equation. Okay, so what I want you to notice is right here, this is our homogeneous case. All right, that's our homogeneous case. And then this one, I think I did it in green, is our y sub p. That's our non-homogeneous. So I need to verify both of those. The first things I'm going to do is I need to verify that this is a fundamental set. So I'm going to find the Wronskian of cosine x sine x so I can show that it is a fundamental set. First showing it being linearly independent. So if I get cosine x, sine x, if I take these derivatives, okay, I get negative sine x cosine x. Thankfully, it's just a 2 by 2. Cosine squared plus sine squared, and that equals 1. That is not 0, so that tells me that they are linearly independent, which tells me that they are a fundamental set, which means the general solution of the, and let's start writing it like this, y sub c. That's my general solution of the homogeneous case. So it's going to be, I think maybe H. I forgot what they use in our book. I don't know why I said C. My brain just spit out a C. We'll just say we'll do homogeneous like that for a moment, okay? So we'll just say that's our homogeneous, and then we'll adapt to the curriculum. My brain's blanking. So here's our general solution for the homogeneous case. I got C1 cosine x plus C2 sine x. Okay, we have shown that. So now what I have to show is that y sub p is a solution to the homogeneous case. All right, this is going to take some derivatives in here that are definitely not pretty. So be very careful. We got to get up to the second derivative. So y sub p derivative, okay, we need two product rules, and there's a chain rule within one. So I get sine x, then the derivative of sine, so I get x cosine x, no sign change. Then I'm going to get negative sine x times ln of cosine x. That's the first part. And then plus, and I keep the cosine x there, times 1 over cosine x times negative sine x. That's the chain rule. Okay, so y sub p, make sure we simplify as far as we can. Okay, do you notice I got this sign canceling, this is canceling, and I'm going to have a negative sign. Those are gone. So I'm going to get x cosine x minus sine x times ln of cosine x. Okay, I got to get to my second derivative. So y sub p, second derivative. It's another product rule. So I'm going to get cosine x minus x sine x. Then the product rule again here, minus cosine x, ln of x, ln of cosine of x, sorry. And then I keep the negative, keep your sign. Then I get 1 over cosine, and then times negative sine again. So I'm going to get y double prime. Does anything cancel? Okay, that's going to, no, things just are gross. Cosine x minus x sine x minus cosine x times ln of cosine x. And then I get plus sine squared x over cosine x. I know I could change that to something, but I think it's gonna, some things are gonna work out in our favor. All right, I'm gonna add now for our general solution. I have y sub p, or not general solution, but we're checking our diffie q, and I need to add these two and get a secant. So y sub prime, double prime, y sub p, said that wrong, y sub p double prime plus y sub p. Okay, and then things are gonna go away, thankfully. That cosine is still there, cosine x. Sine x goes away. The weird negative cosine ln is going away. And then I just get left with a sine squared x over cosine x. Okay, that's just cosine squared x over cosine x plus sine squared x over cosine x. Well, the top's just going to add to 1. The bottom is a common denominator, so keep it. And that ends up being a secant x. So we have proved it that that is our y sub p is a solution. So the general solution overall is going to be y sub, it's c. I remember now. It is c. So let's go back up there. You guys change this h to a c. My brain did remember it correctly. I totally put it together. It's complementary homogeneous function. I think they worded up here associated. They start using a different word. We'll see. I've taught this out of a different book, and that's what they were using. Okay, we have one more that's like this, and that'll be the end of this video. Right. So verify that the given two parameter um, family of functions is the general solution of the non-homogeneous differential equation on the indicated interval. So we have that. And this is going to be the same type of thing. So the y sub c, that's the complementary homogeneous solution, right, is going to be c1 x to the negative 1/2 plus c2 x to the negative 1. So we are going to need to show that that forms a fundamental set, the two solutions that come from that. So we have y1 is x to the negative 1/2, y2 is x to the negative 1. So to show that they are a fundamental set, I got to use the Wronskian. I don't think we're going to need a lot of space here. So Wronskian of y sub 1, y sub 2, that's going to be equal to x to the negative 1/2, x to the negative 1. We only need one derivative down since there are only two. So I got negative 1/2 x to the negative 3/2. And then I got negative x to the negative 2. All right, if I were to multiply that out, we just got to be careful. First, the forward slash diagonal, or I guess it's a backslash. Backslash. I get negative x, and it's a negative 2 and a negative 1/2. So that's a negative 5/2. Plus, because it's going to be a minus, but I got a plus and minus there. So plus 1/2. And then this is going to be an x to the negative 5/2. So together, it would be 1/2 x to the negative 5/2, which is not 0, which implies that they are linearly independent, which implies that they are fundamental set. A fundamental set of solutions. So our y sub c is exactly what we said it was. c1 x to the negative 1/2 plus c2 x to the negative 1. Okay, so we verified that part. All we gotta do now is verify the particular solution part. So y sub p, okay, is gonna be this back half here. So 1/15 x squared minus 1/6 x. So now we just have to verify this with the non-homogeneous. I'm going to write it again because it's not as simple as the one we just did. 2x squared y prime double prime plus 5x y prime plus y, and this should equal x squared minus x. All right, so I like to build up to it. So I have y sub p, so I'm going to go ahead and do y sub p prime. Going to find that. So that's going to be 2/15 x minus 1/6. And then I like to go ahead and get my 5x y sub p prime. So I can just go ahead and highlight them all and add them together. So if I do times 5, I get 2/3x minus 5/6. Right? And then I'm going to need y double prime. That's 2/15. And we need to do 2x squared times y double prime of p, which is just going to be 4/15 x squared. All right, so left-hand side is equal to 2x squared y prime plus 5x y prime. I said prime, but I meant double. And that's going to equal, and we can go ahead and just highlight these and add them together. There, here, and there. Those three things. All right, if I add them together, okay, I got 4/15 plus 1/15 x squared. I feel like I'm missing something. Oh, hey, this should be an x squared and this should be an x. I never multiplied it through. All right, so there we go. That fixes things. I was like, kind of panicking. So 1/15 and 4/15 is 1/3 plus the 2/3 gets me x squared. And then I got negative 1/6 and negative 5/6, which gives me a negative x. And we have verified, and our general solution is y sub c and y sub p. So we have verified it. So this is going to be a technique that we're going to be using moving forward, is we are going to have to try to find the solutions to the homogeneous, however you want to say it. And then we're going to have to try to find a solution to the non-homogeneous case and then add them together to get general solutions. So we have quite a bit of work ahead of us, but at least I hope this helps us understand how to get to these points before we actually start the solving. All right, I believe there's like one more section, one more video in this section, and that will be it.